University of Munich. It's a new institute. Today I'm going to talk about graph representation learning, embedding multimodality BIM models into graphs. It's actually an extension of the previous BIM, foundation models discussion, but more from the technique perspective. This is a collaboration work with Technion, Dr. Huaquan Ying. We already have a lot of machine learning studies in the BIM domain, like BIM object classification is a pretty popular task. Like BIM models are compiled as images, as tables, as meshes, and other formats, then they are going to fade into the deep learning models. And we think this is an inverse approach compared to what computer vision and natural language processing, those two domains they have done. We call it inverse because researchers in our domain say lack algorithm first, such as the first example here. Oh, sorry for that. Sorry for this.
Do we have a technician here? Probably EC3, EC3. Oh no. Ready to...
I want to point to something, then it's kind of locked.
Okay, that's not what a computer is for, to point at something.
Yeah,
that's too complicated.
You have pointer here, you know.
Yes.
Okay, we need to wait now. I think Marta is getting one of the technicians.
Really sorry for that. Maybe you can have an audio track and go on. Introduce GNI or...
Yeah, no problem. So actually, we call it is an inverse research approach because not like in computer vision, they already use the matrix to store the image information into a very structured matrix and then design a series of algorithms such as neural network to process the feature of this data. Yeah, thank you. So then this kind of, for example, using MVCN as example, so researchers in our domain, first of all, convert those kind of mesh or rendering those mesh and generate images and then input them into MVCN for classification, got the results, evaluate the accuracy. During this approach, we ignore the complexity and the richness of BIM models. And one of the results come from those studies where those kind of work is really hard to be generalized to a wider scope. So if we really look at the BIM model here, so we go to the fundamental of the data modality perspective. Actually, it's pretty simple to understand. They have several modalities, such as it has geometry. Geometry gives our vision information, gives the location, gives the dimension. It has object semantics, such as material, such as height, these attributes. And objects, they also have a relationship. Wall could be context another wall. And we have many other documents, such as drawings, such as codes. So basically, we have many heterogeneous data in BIM. So the first question we ask ourselves is that, what kind of data format that can really leverage or integrate those kind of multimodality data and can be represent those multimodality data of BIM. And if we can find the data format, just like find the matrix for images, what kind of following techniques do we need to process this data? So we propose a framework. Here we adopt graphs. We call it building information graphs. First of all, we use modalities to describe the model. Geometries, attributes, relationships, and other data. Then we use graphs to represent and integrate all the information together. Inside the graph, the nodes could be the BIM objects, and the attributes of the node could be the attributes of the object. And we use relationships to link them together. And some other data, like geometry, which might not be suitable for graph representation, then we keep it as is file format and use a virtual link back to this graph. So this graph can contain all the heterogeneous information that you can access through it. Then we are going to embed those heterogeneous information from human understandable format into a very long, very dense vectors that in a very high dimensional space. This process, embedding, is going to let the computers understand the design, just like an expert. After embedding, we are going to put like the learning algorithms, such as graph neural network, on top of the embeddings to discover the possible statistic patterns. Then we put the task head at the end. And all those tasks, such as node classification, link prediction, under the graph learning context, should be not standing alone. They should serve for the application in this domain, such as node classification. They can enhance the interoperability, such as link prediction. Link all those data together. They can also enhance collaboration. Generating new nodes, generating new edges could support the generative design. This is the framework of building information graphs. And in this conference paper, we explore the first part, graph representation learning. Just similar like task embedding to tokens. So graph representation learning aims to map those design information, those heterogeneous data, including attributes, geometries, relationships, into a uniform, dense vector space that can, ideally, that can be understood by the computers. And we choose the graph representation learning style because it's the first step to validate if graph could be the learning suitable format for machines. And it's also a very fundamental steps to serve for the downstream for the following task. So here is what we do. We extract all the attributes, the modalities from BIM models. Regardless IFC or Revit models, we just extract the modality into geometry, classes, attributes, and topology. Then we are going to embed those modalities one by one. We use zamping techniques to embed the geometries, and we use large language models to read the attributes and generate the text embedding. Following that, we concatenate these two modalities embedding together. Until now, we didn't consider the topology yet. So we use another GNN to leverage the topology and update this kind of embedding. After the output of the GNN already merge and leverage those three embeddings from the BIM models. At the end, we use a node classification task to test if this embedding is effective or not. To validate this idea, we constructed an initial dataset contains 5 models from different use and scenarios. And these models contains 15 IFC classes and more than 20,000 nodes and 100,000 edges. And those edges could be heads, hosts, touches, and intersects. Here is the initial results. We group into 2 groups. The first group from number 1 to number 4. Here, we keep the graphs all connected, keep all the edges connected. Then we are going to iterate the node embeddings and to say which one is effective and which one is not. So number 1 contains both attribute embeddings and geometry embeddings. Again, attribute embeddings generated by large language models, geometry embeddings generated by geometry zamping. And then you can see the results is pretty interesting. When we consider all the embeddings here, the accuracy achieves almost 87%, which is lower by only consider the attributes embedding. So from the first 4 experiments, we observed that the text embedding by large language model is pretty effective, while the geometry zamping techniques is not. For the following 3 experiments, we are going to remove all the node embeddings. We are going to understand if the edges, if the relationship of the graphs that we talk a lot, will they really contribute to the performance? So we start with very little relationship and increase the types of relationships. And as you can see, when we only consider one type of relationship has, the accuracy is around 47%. When the relationship types increase, the graphs are more interconnected with each other. The performance has been boosted more than 10%. So from this perspective, we can partly answer the first question. Maybe graphs is a considerable format that can leverage the topology and contribute to the performance. Of course, we are going to improve the work by kind of like improve the embedding techniques for each modality as well as they will how to merge them together. But more importantly, we are constructing a larger BIM dataset. There's still a collaboration work between Technion and TUM. And until now, we already collect more than 1,500 models. And most of them federated models and diverse scenarios, diverse LODs, and diverse qualities. we are going to clean these models now. We are, like ImageNet, we are going to design the software, cleaning software in a web-based level and going to distribute around different countries and add more and more people to involve for labeling this data set. And we are aiming to share this data set with the community in the future. So in short, some key takeaways. Here we propose the learning framework for building information graphs, and we have another paper which introduces the concepts of bigs, which will come very soon. And in this conference paper, we introduce graph representation learning. Here we explore how to embed multimodality design data into high-dimensional vectors, and that can facilitate graph learning. And this initial results shows that the performance of the experiment has been improved a lot by leveraging relationships, by considering graphs. And another conclusion we got is that large language models are very effective to embed text attributes. Thank you very much.